When people think about what physics is, they typically imagine it as a search for answers. What is the universe made of? How do planets move? What is light? Physics textbooks are filled with answers, with equations and laws and constants that seem to represent final truths about nature. Students memorize these answers, plug numbers into formulas, and solve problems that have definite solutions. But I must tell you something that may seem strange coming from someone who has spent his life in physics. Physics is not fundamentally about answers at all. It is about questions. The quality of the questions we ask determines the quality of the understanding we achieve, and recognizing which questions are meaningful and which are not is more important than having answers to every question we might formulate. Let me explain what I mean through the story of my own work, because I came to this realization gradually through confronting the puzzles of quantum mechanics. When I first began studying atomic structure in 1912, I thought my job was to find answers. What holds atoms together? Why are they stable? What determines the wavelengths of light they emit? These seemed like straightforward questions that should have straightforward answers. I developed my atomic model that gave numerical answers to these questions. I could calculate the energy levels of hydrogen. I could predict spectral wavelengths to many decimal places. These answers were extraordinarily successful, matching experimental measurements with remarkable precision. But even as I celebrated this success, I was troubled because I did not truly understand the answers I had found. I had imposed quantum rules, restrictions on allowed orbits, without knowing why these rules held. I had answers without deep understanding of the questions. As quantum mechanics developed through the 1920s, I began to realize that some of the questions I had been asking were not actually well posed. When I asked where exactly an electron is in an atom, I was presupposing that position is a property that always has a definite value. But quantum mechanics revealed that this presupposition is wrong. Between measurements, an electron does not have a definite position. It is described by a wave function giving probabilities for different positions. The question where is the electron right now presumes a kind of definiteness that does not exist in quantum states. This forced me to think very carefully about what questions are meaningful in quantum mechanics. I could meaningfully ask what is the probability distribution for the electron's position, or if I measure position, what value will I find, or what is the wave function describing the electron's state. These are good questions with definite answers. But the apparently simple question where is the electron in itself has no answer because it presupposes a classical definiteness that quantum systems do not possess. Werner Heisenberg's uncertainty principle brought this issue into sharp focus. The principle tells us that we cannot simultaneously specify precise values for position and momentum. This is not because we lack information but because these quantities cannot both have precise values at the same time. So if I ask what are the exact position and exact momentum of this electron right now, I am asking a question that has no answer. The question itself is flawed because it assumes something about reality that is not true. This was deeply unsettling to many physicists. Albert Einstein in particular felt that if a question could be clearly formulated, it should have an answer, and if physics could not provide that answer, physics was incomplete. When Einstein asked what properties a particle has between measurements when we are not looking at it, he expected there should be definite answers to this question even if we could not access them. He believed there must be hidden variables, unobserved properties that determine everything even though quantum mechanics does not describe them. But I came to believe that Einstein was asking questions that have no answers because they rest on false assumptions about how nature works. The question what is the particle's position when we are not measuring it presumes that position exists as a definite property independent of measurement. But quantum mechanics says this presumption is wrong. The particle does not have a definite position between measurements. It has a quantum state described by a wave function, and this state does not include definite values for all classical properties. Learning to recognize which questions are meaningful and which are based on false presuppositions became central to my understanding of quantum mechanics. This is what I meant by complementarity. I was not just saying that we have incomplete knowledge or that we must be satisfied with partial answers. I was saying that some combinations of questions cannot simultaneously have answers because the properties they ask about are complementary, and cannot both be definite at once. Can you tell me the electron's position and momentum? No, because these are complementary properties that cannot both be precise simultaneously. Did the electron go through the left slit or the right slit in a double-slit experiment when we did not observe its path? This question has no answer because the electron was in a superposition of both paths, not definitely going through one or the other. Does the electron behave as a wave or as a particle? Neither description alone is complete, and both are needed, but they apply to different experimental contexts and cannot be combined into a single consistent picture. These are not failures of physics to provide answers. They are recognitions that the questions themselves are inappropriate, that they import classical assumptions that do not apply to quantum systems. The art of doing quantum mechanics well involves learning to ask good questions, questions that respect the actual structure of quantum reality rather than imposing classical expectations. I spent many hours discussing these matters with colleagues at my institute in Copenhagen. We would debate late into the night about which questions were meaningful, which presupposed classical concepts that did not apply, which could be reformulated in better ways. These discussions were not about finding answers but about refining questions, about understanding what we could meaningfully ask of nature and what kinds of questions led only to confusion. Let me give you an example of how reformulating questions leads to deeper understanding. Instead of asking where is the electron, which presumes definite position, we can ask what is the wave function of the electron. This is a better question because it asks about what actually describes the quantum state. The wave function gives us all the information that exists about the electron's potential positions, momenta, and other properties. It does not give definite values for classical quantities, but it gives us the quantum description from which we can calculate probabilities for any measurement we might perform. Or instead of asking did the radioactive atom decay at this exact moment, which presumes a definite decay time that does not exist, we can ask what is the probability per unit time for decay, or what is the half-life of this isotope. These questions have precise answers. The first question, asking for a definite decay moment, has no answer because quantum mechanics says the decay time is fundamentally random and not predetermined by any property of the atom. This shift from seeking answers to refining questions represents a profound change in how we think about physics. In classical physics, we assumed that all well-formed questions about physical systems had answers, and if we could not find the answers, it was due to our ignorance or inadequate theories. But quantum mechanics teaches us that nature herself determines which questions have answers. Our job is not to demand answers to every question we can formulate, but to discover which questions nature permits us to answer and to understand why other questions cannot be answered. This may sound like a retreat, like giving up on the goal of complete knowledge. But I see it differently. Understanding which questions can be answered and why is itself profound knowledge. Knowing that position and momentum cannot both be precise is not ignorance. It is understanding something deep about the structure of quantum states. Knowing that we cannot ask which slit the electron went through while simultaneously observing interference is not a limitation but an insight into complementarity. The questions we ask also determine what experiments we design and what we learn from them. If I ask, can I simultaneously observe wave and particle properties? And I understand that the answer is no due to complementarity. This tells me something crucial about how to design experiments. I must choose which aspect to observe, knowing that the experimental arrangement needed to observe one aspect precludes observing the other. The question guides the inquiry in productive ways precisely because I understand its limits. There is also the matter of questions that are meaningful but whose answers are probabilistic rather than deterministic. When will this particular radioactive atom decay? Quantum mechanics can give me a probability distribution over possible decay times, but it cannot give me a definite answer for when this specific atom will decay. Is this a failure to answer the question? I would say no. The probabilistic answer is the complete answer that nature provides. Demanding a more definite answer reflects a misunderstanding of how quantum mechanics works. Einstein famously objected to this, saying that God does not play dice with the universe. He felt that probabilistic answers were incomplete, that there should be deeper deterministic answers if only we looked hard enough. But experiments testing Bell's inequalities have shown that Einstein's hope for hidden variables providing deterministic answers is incompatible with observed reality. Nature really is probabilistic at the quantum level. The probabilistic answers are not placeholders for missing deterministic answers. They are the complete answers to the questions we ask. This requires a certain intellectual humility, an acceptance that our classical intuitions about what questions should have answers and what kinds of answers they should have must yield to what nature actually shows us. We cannot impose our preferences on reality. We must discover what questions reality permits, and what kinds of answers she provides. There is something liberating about recognizing that physics is about questions rather than answers. It means that inquiry never ends, that there is always more to understand about which questions to ask and why. When I thought physics was about finding final answers, I sometimes felt that once we had the answers, the work would be complete, the mystery dissolved. But recognizing that the challenge lies in formulating good questions means the work is never done. Each answer opens up new questions, and refining our questions is an ongoing process. Consider the question, what is light? For centuries, physicists debated whether light was waves or particles. They sought a definitive answer. But quantum mechanics revealed that this question, in its either-or form, has no simple answer. Light has both wave and particle properties that manifest in different experimental contexts. The right question is not what is light, but how does light behave under different circumstances? What properties does it exhibit in different experimental arrangements? This reformulation acknowledges complementarity and leads to productive inquiry rather than sterile debate. Or consider what happens during a quantum measurement. This question has occupied physicists for a century. We have many answers, many interpretations, but no consensus on a final answer. Why? I would suggest it is because the question, as typically posed, may not be as well defined as it seems. What exactly constitutes a measurement? Where is the boundary between quantum system and classical apparatus? These subsidiary questions turn out to be crucial, and different ways of addressing them lead to different interpretations of quantum mechanics. Perhaps instead of seeking a final answer to what happens during measurement, we should ask more specific questions. What predictions does quantum mechanics make about measurement outcomes? How does the wave function change when measurement occurs? What role does decoherence play in suppressing quantum interference in macroscopic systems? These more targeted questions have clearer answers and lead to productive research, even if the grand question remains philosophically contentious. I have come to believe that much philosophical confusion about quantum mechanics arises from asking questions that presuppose classical concepts that do not apply. Does the wave function represent physical reality, or merely our knowledge? This question assumes a sharp distinction between reality and knowledge that may not hold in quantum mechanics. Is the electron really in two places at once in a superposition, or is it definitely in one place with us just not knowing which? This question presumes that definitely in one place and in a superposition are the only options, but quantum mechanics offers a third option that is either. The skill of asking good questions is not something that can be reduced to a formula. It requires deep engagement with the subject matter, careful attention to the concepts being used, awareness of hidden assumptions, and willingness to revise questions when they prove to be poorly posed. This is why physics is as much an art as a science. The scientific method provides tools for testing answers, but discerning which questions to ask in the first place requires judgment, intuition, and conceptual creativity. Throughout my career, I have tried to cultivate this skill in myself and in the students who came to work with me in Copenhagen. I encouraged them not to accept questions uncritically but to examine the assumptions behind them, to consider whether classical concepts were being inappropriately applied to quantum systems, to reformulate questions in ways that better match the structure of quantum mechanics. Some found this approach frustrating. They wanted clear answers, not perpetual questioning of the questions. But those who persevered often achieved deep insights. One of the most important questions in quantum mechanics is not about any specific physical quantity, but about how to interpret the formalism itself. What does the wave function represent? What is the nature of quantum states? What is the role of measurement? These foundational questions have been debated for a century, And while we have made progress, we do not have final answers that satisfy everyone. Does this mean physics has failed? I would say no. It means we are still refining our questions, still learning how to ask about the foundations of quantum mechanics in productive ways. Different interpretations of quantum mechanics represent different ways of formulating questions about quantum foundations. The Copenhagen interpretation, which I helped develop, emphasizes the role of measurement and complementarity. The many worlds interpretation asks what if the wave function never collapses and all possibilities are realized in different branches. The pilot wave theory asks what if particles have definite positions guided by a quantum wave. These are not competing answers to the same question but different questions reflecting different conceptual priorities. I have my own preference, naturally, for the Copenhagen approach, but I recognize that other formulations ask interesting questions and have their own insights. The plurality of interpretations is not a weakness but a sign that we are still exploring conceptual space, still discovering which questions lead to fruitful understanding and which lead to dead ends. This openness to multiple approaches to formulating questions is itself valuable. The emphasis on questions over answers also helps explain why physics does not proceed linearly toward complete knowledge. We do not simply add more answers to an ever-growing list. Instead, we periodically reconceive what questions to ask. Newton asked how objects move and gave us laws of motion. But then Einstein reformulated the questions, asking about the nature of space and time themselves, and found that Newton's answers were approximations within a deeper relativistic framework. Quantum mechanics reformulated questions about atomic structure, showing that classical questions about electron orbits presupposed a definiteness that does not exist. Each revolution in physics involves not just new answers but new questions. Recognition that old questions were based on faulty assumptions and need to be replaced with better questions. Progress is not just accumulating more answers but learning to ask better questions that reveal deeper structures of reality. If physics is about questions rather than answers, what does this mean for the goal of physics? Is there an endpoint, a final theory that answers all questions? I am skeptical. I suspect that as we probe deeper into nature, we will continue to find that our questions need refinement, that assumptions we took for granted need revision, that new phenomena require new conceptual frameworks. The process of learning to ask better questions may be unending. But this is not cause for despair. The joy of physics lies not in reaching a final destination but in the journey of inquiry itself, in the intellectual struggle to understand nature more deeply, in the satisfaction of asking a good question and finding that nature provides an answer, or in recognizing that a question we thought was meaningful turns out to be based on false premises and needs to be reformulated. This is the creative work of physics, and it is never finished. When students ask me how to become better physicists, I tell them that learning to ask good questions is as important as learning to solve problems or master mathematical techniques. Read deeply. Think carefully about the concepts you are using, be alert for hidden assumptions, do not be afraid to question questions themselves. Physics rewards those who can see beyond the obvious questions to deeper questions that illuminate the structure of reality. The reason physics is about questions rather than answers is that answers are always provisional, always context-dependent, always subject to revision as our understanding deepens. But good questions endure. The question of how to reconcile the wave and particle nature of light led to quantum mechanics. The question of what determines atomic stability led to my atomic model and eventually to the full quantum theory. The question of what observation means in quantum mechanics continues to generate insight a century later. Questions drive progress. Answers mark temporary resting points. So when I say physics is about questions, not answers, I am not being paradoxical or mystical. I am stating what I have learned from a lifetime of engagement with the deepest problems in physics. The answers matter, certainly. They must match experiment, must be mathematically consistent, must guide practical applications. But the answers we have reflect the questions we asked, and better questions lead to deeper answers. The ultimate skill in physics is learning to ask questions that reveal the true structure of nature, and this skill is acquired through experience, reflection, and willingness to question everything, including the questions themselves.